A black hole is the universe's ultimate cosmic trap. Nothing, not even light, can escape its pull once it crosses the boundary. But what if the opposite existed? What if there was a place in space where nothing could ever enter, only violently erupt? This is the white hole, a theoretical monster that is the bizarre, inverted mirror of a black hole. By the end of this exploration, you will understand why this speculative idea forces us to rewrite the rules of reality itself. We will journey to the edge of known physics, where time may run backwards and the Big Bang itself might be seen in a shocking new light. What is the most beautiful, impossible thing you believe the universe could hide? That reversed rule is the perfect starting point. A white hole is defined by a single, simple, and utterly bizarre principle. It is a region of space-time where nothing, absolutely nothing, can ever enter from the outside. While a black hole's event horizon is a one-way door inward, a white hole's horizon is a one-way door outward. Matter and energy can only be violently expelled from it. You could fly a spaceship right up to its boundary, but you could never cross it. The universe itself would seem to push you away. This isn't just a fun idea for science fiction. It comes from the same mathematics that predicted black holes in the first place. Einstein's equations of general relativity, which describe how mass and energy warp the fabric of space and time, are symmetrical. They work forwards and backwards, the equations that give us the black hole solution, a pit in space-time that only swallows, also mathematically allow for a white hole solution, a fountain in space-time that only spews. They are two sides of the same cosmic coin, one the perfect mirror image of the other. Think of a black hole as a cosmic drain pulling everything in. A white hole, then, would be that same drain running in reverse, with water and debris erupting upward with impossible force. One is the ultimate consumer. The other would be the ultimate producer. So if the math allows it, and it seems like a perfect counterpart to something we know exists, why have we never found one? The answer lies in a conflict between the beautiful symmetry of mathematics and the messy, one-way street of reality as we experience it. The mathematical heart of this mirror universe is surprisingly elegant. To understand a white hole, we must first look deeper at the map we use for a black hole. In 1916, Carl Schwarzschild found a solution to Einstein's equations describing a perfectly spherical, non-rotating mass. This solution gave us the classic picture of a black hole with its event horizon and central singularity. But for decades, physicists viewed this solution as a kind of mathematical curiosity, a description of a frozen star. They only looked at the part of the map that represented the outside universe and the point of no return. It was like having a map of a tunnel but only studying the entrance, refusing to consider what might be on the other side. Then, in the 1960s, physicists like Martin Kruskal and George Shekars decided to extend the map. They created new coordinates, a new way of drawing the space-time diagram that didn't break down at the event horizon. This maximally extended map revealed the full, shocking landscape hidden in the mathematics. The map didn't just show a pit. It showed a structure with two separate, disconnected universes, linked by a tunnel called an Einstein-Rosen bridge, what we popularly call a wormhole. And crucially, it revealed two distinct one-way membranes. One is the black hole event horizon we know, where everything falls in from our universe, but the map showed another horizon in the other universe. And the rules there are perfectly reversed. That second horizon does not allow anything in. It only allows things out. In this complete mathematical picture, that is the white hole. It is not a separate object floating in our cosmos. It is literally the other end of the black hole tunnel, the exit door that spews matter into a completely different universe. Think of it as a one-way street system connecting two cities. From our city, all the traffic flows into the tunnel entrance, the black hole. It is impossible to drive back out the way you came. But on the other side, in that other city, the traffic only flows out of the tunnel exit, the white hole. No car from that city can drive into the exit. The street sign is permanently flipped. This is the pristine mathematical prediction. A black hole in our universe is connected to a white hole in another universe, with a fleeting wormhole bridge between them. The equations are perfectly time-symmetric. They treat past and future as equals. So if a black hole, a future trap, can exist, then its past mirror, a white hole, must be possible in the math. But mathematics describes possibilities while physics demands realities. And the reality, as we observe it, seems to have a profound preference for one direction over the other. This elegant mathematical map presents us with a breathtaking possibility. The white hole is not floating alone in the void. According to this maximally extended solution, it is inextricably linked to its dark twin by the most famous shortcut in science fiction, a wormhole. Specifically, it forms what is known as an Einstein-Rosen bridge. In this model, the singularity of a black hole and the singularity of a white hole could be connected by a tunnel through the very fabric of spacetime. Imagine our cosmic drain, the black hole, not emptying into a pipe that goes nowhere, but instead connecting to a pipe that leads to a cosmic fountain erupting in a distant location. Matter that falls into the black hole in our region of the cosmos could, in theory, be violently ejected from the white hole somewhere else. The thrilling narrative potential is obvious. This could be the universe's ultimate transportation system, a one-way ticket to another place or even another universe entirely. A journey through such a bridge would be the most extreme voyage imaginable. An astronaut crossing the black hole's event horizon might, for a fleeting instant, find themselves in the tunnel, the wormhole, before being carried by the inexorable flow of space-time out through the white hole's erupting horizon into a new and foreign cosmos. It is the perfect plot for an epic saga, yet this is where the cold laws of physics interrupt our grand story. The wormhole in this pristine mathematical picture is notoriously unstable. It is more of a theoretical connection than a practical highway. Calculations suggest it would pinch off and collapse into a singularity faster than anything, even light, could possibly travel through it. The bridge would snap the moment you tried to cross. So while the mathematics generously offers us this incredible linked structure, a black hole here connected to a white hole there, our current understanding of physics slams the door on using it for travel. It appears to be a beautiful closed loop, but what if that loop isn't just a mathematical artifact? What if it describes a real cosmic recycling process? This elegant mathematical symmetry runs headlong into one of the universe's most unbreakable rules. That rule is the second law of thermodynamics. It states that in any closed system, the total amount of disorder, called entropy, must always increase or stay the same. It is the reason your room gets messy over time, the reason ice melts in your drink, and the ultimate reason time has a direction we can all agree on. Things move from order to disorder. Now consider our white hole. It is a region of space that spontaneously and violently ejects organized matter and energy out into the universe. From the perspective of the outside cosmos, it looks like a source of pure, low-entropy order appearing out of nowhere. This presents a profound problem. A white hole seems to be a cosmic machine that decreases the overall entropy of the universe, violating the second law at its core. For most physicists, this is the single biggest reason to doubt the physical reality of white holes. The universe simply does not work that way. You cannot have a fountain of order erupting into a cosmos that is irrevocably sliding toward disorder. It would be like finding a waterfall that flows upward, defying gravity. Our experience tells us such a thing cannot exist. This starkly contrasts with the black hole, which has been beautifully woven into the fabric of thermodynamics. Thanks to the work of Stephen Hawking and others, we now understand that black holes are not eternal. They evaporate over astronomical timescales through a process called Hawking radiation. More importantly, black holes possess entropy themselves. A black hole is the ultimate sink of disorder. When matter and energy fall in, the entropy of the outside universe effectively increases, perfectly obeying the second law. The black hole is a thermodynamic object playing by the established rules of the cosmos. The white hole, in its classic form, does not play by those rules. It appears to be a thermodynamic rebel, a mathematical ghost that the real universe would immediately reject. This fundamental clash is why many scientists label white holes as unphysical. They are a stunning possibility written in the equations of gravity, but seemingly vetoed by the deeper laws of heat, energy, and time's arrow. So does this mean the story ends here? Is the white hole merely a beautiful mistake in our math, destined to be crossed out? Not necessarily. Some of the most daring ideas in modern physics suggest we might be looking at this puzzle from entirely the wrong angle. Perhaps the white hole isn't a rebel but a relic. To find a place for it in our cosmos, we must look not to the distant future but to the absolute beginning. The most profound connection lies in the moment of creation itself. What if the Big Bang was not just a singular event but a white hole in action? Consider the description. Our universe erupted from an initial state of unimaginable density and temperature, a singularity from which all matter, energy, space, and time began expanding outward. Nothing existed before to fall into it. Everything we see came streaming out. This is not just a vague similarity, it is the precise operational definition of a white hole. The Big Bang singularity is a point in our past that we can never revisit or send information back into. It is a one-way boundary in time, an exit-only door for reality itself. In this radical view, our entire observable universe is not just the aftermath of an explosion. It is the ongoing eruption from a cosmic white hole that began nearly 14 billion years ago. This reframes everything. We are not floating in the debris of a random blast. We are living inside the continuous, expanding output of a primordial white hole event. The universe isn't merely expanding, it is still being born, still flowing outward from that impossible source. This idea offers a startlingly elegant symmetry. If black holes are in points where matter and information vanish, then the Big Bang, a white hole, is the corresponding starting point where everything appears. One is the ultimate sink, the other the ultimate source. They could be the two fundamental bookends of cosmic existence. This leads to even more speculative yet breathtaking possibilities. Some cosmological theories, like the Big Bounce, propose that our universe is part of an endless cycle. In this model, a previous universe collapses into a giant black hole, whose singularity then becomes a white hole, birthing a new universe in a new Big Bang. Our cosmos would be one link in an infinite chain, breathing in and out through phases of gravitational collapse and explosive rebirth. Another profound idea is conformal cyclic cosmology, proposed by physicists like Roger Penrose. It suggests that as our universe expands and cools over trillions upon trillions of years, all matter will eventually decay and black holes will evaporate, leaving a vast, empty, featureless sea of low-energy particles. In this ultra-smooth state, the universe loses all sense of scale. The infinite future of one cycle becomes geometrically identical to the ultra-dense beginning of another. The end becomes a new beginning, with a white hole-like Big Bang emerging from the ashes of the previous eon. In these visions, white holes are not rogue objects but essential cosmic organs. They are the transformation points, the gates between cosmic generations. The violent, creative fury of a white hole is not a violation of thermodynamics on a universal scale, but the reset button for the entire system. It is the moment when the story starts again, with new physical constants, new laws perhaps, and a fresh canvas for existence. This places our universe within a narrative far grander than we ever conceived. We are not the first and only chapter. We are a single verse in an epic poem that has no beginning and no end. But where does this leave the white hole in our collective imagination? While physics wrestles with its plausibility, science fiction has embraced its potential with open arms. The very concept of a cosmic object that defies entry and erupts with creation is a storyteller's dream. It becomes more than a theory, it becomes a narrative device of immense power. In the rebooted series of Doctor Who, the episode The Satan Pit presents a chilling version. The Doctor and his companion Rose find themselves on a base orbiting a black hole, only to discover a malevolent entity imprisoned on a planet below. The story reveals this entire impossible setup. A planet surviving at the edge of a black hole is maintained by a white hole on the opposite side, providing the necessary energy and stability. Here, the white hole is a cosmic battery and an anchor, a source of power so profound it can cage the devil himself. It is portrayed not just as an astronomical object, but as a fundamental force for balance in the universe. An earlier and wonderfully eccentric example comes from the cult classic The Adventures of Buckaroo Banzai. In this film, the villainous alien red lectroids from Planet 10 need a rare element to power their war machine. This element, they explain, can only be found in the 8th dimension, and the only way to reach it is by traveling through a white hole. In this wild narrative, the white hole is explicitly a gateway, a dimensional portal to realms beyond our own. It is the ultimate shortcut, a plot device that unlocks the entire cosmos for adventure. These portrayals, while taking enormous creative license, touch on the core conceptual implications of the theory. They visualize the white hole as a source of infinite energy, a bridge to other realities, or a cosmic reset button. They ask the same questions physicists do, but through the lens of drama and wonder. What if we could tap that erupting energy? What if it led somewhere? What if it could rewrite the rules of a local reality? Science fiction uses the white hole to explore themes of origin, destiny, and the fragility of natural law. By placing human characters, or alien ones, in confrontation with such an object, these stories make the abstract theory emotionally tangible. We feel the awe and the terror of confronting a law of physics made manifest. This cultural journey does more than just entertain. It popularizes the idea, planting a seed of cosmic possibility in the public mind. Long before someone encounters the complex mathematics of general relativity, they might have seen the Doctor staring into the abyss or heard Buckaroo Banzai talk about trans-dimensional travel. These stories create a conceptual framework, a sense of familiarity with the bizarre. They remind us that the universe's greatest mysteries are not just equations on a chalkboard, but potential landscapes for epic tales of survival, curiosity, and discovery. The white hole in fiction, in all its varied forms, serves as a testament to human imagination's need to go where science is still cautiously stepping. It asks us to dream first and calculate later. The ultimate test for any cosmic theory lies in the cold, hard data of the night sky. For white holes, the search is not for the object itself, but for its explosive signature, the final, violent death rattle it might emit. Astronomers have a candidate in mind for such a cosmic scream, the gamma-ray burst. These are the most energetic explosions in the universe since the Big Bang, fleeting blasts of intense high-energy radiation that can outshine entire galaxies for a few seconds. The leading theories for their origins involve the collapse of massive stars or the merger of ultra-dense objects like neutron stars. But what if a small, ancient few were something else entirely? This is where the concept of a primordial white hole enters the search. The idea is that in the extreme conditions of the very early universe, tiny, microscopic knots of spacetime could have been pinched off, forming not just primordial black holes, but also their theoretical opposites. These hypothetical primordial white holes would have been ticking cosmic clocks, not made of matter, but of pure spacetime geometry. Over eons, according to some extensions of quantum gravity theories, they would not slowly evaporate like black holes, but could become unstable. Their entire existence, a state of perpetual eruption held in check by gravity, might reach a breaking point. The result would be a catastrophic, total disintegration. In one magnificent, irreversible instant, all the energy and potential trapped within its one-way horizon would be unleashed in a titanic flash. The energy released would be staggering, channeled into a beam of high-energy gamma rays and other radiation. To a telescope, this event could look remarkably like a certain type of gamma-ray burst, one that appears from nowhere in a region of space with no visible progenitor star or galaxy, and then vanishes forever, leaving no remnant behind. It would be a one-off event of incomprehensible power with no conventional explanation. Fast radio bursts, those mysterious millisecond-long blips of radio waves from across the cosmos, have also been speculatively linked to such phenomena. While the evidence is entirely absent so far, this speculative link provides a crucial service. It transforms the white hole from a purely mathematical ghost into a potential physical entity with a predicted observational fingerprint. It gives astronomers a specific, if extraordinarily faint, signal to hunt for in the torrent of cosmic data. Every time a new, bizarre, and unexplained flash appears in the sky, a small group of theorists might wonder, if only for a moment, if they are witnessing the final, defiant shout of a white hole, a theoretical monster breathing its last after holding the universe at bay for billions of years. The search for a white hole's death cry leads us to an even deeper mystery, one that strikes at the very foundation of reality. This is the black hole information paradox, and its potential solution might require the very existence of something like a white hole to make sense. The paradox is devastatingly simple. According to Einstein's general relativity, when something falls into a black hole, all its information, the specific arrangement of particles that made it a book, a planet, or a person, is crushed into the singularity and lost forever. But quantum mechanics, the other pillar of modern physics, insists that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but never erased. So which law breaks? Does the universe have a permanent, one-way shredder, or is our understanding of spacetime fatally flawed? This is not a minor technicality. It is a fundamental crisis that suggests our two most successful theories of reality are fundamentally incompatible. Resolving it might demand a complete rewriting of physics. Some of the most radical proposals to save information invoke structures that look suspiciously like white holes. One idea is the firewall. To preserve information, the event horizon of a black hole might not be a smooth, empty space as Einstein predicted. Instead, it could be a searing wall of high-energy particles, a literal firewall that incinerates anything crossing it. This firewall acts as a dramatic transformation point, not unlike the violent boundary of a white hole, preventing anything from truly entering the classical interior and instead scrambling its information into radiation. Another proposal from string theory is the fuzzball. In this view, a black hole is not a vacuum with a point singularity at its heart. It is a dense, tangled ball of strings, its surface a fuzzy, quantum structure that extends to where the horizon should be. There is no inside, no tunnel, no separate singularity. The information of everything that falls in is smeared across this complex surface. Crucially, some fuzzball solutions can exhibit white hole-like behavior, momentarily erupting or displaying quantum signatures that mimic an exit-only boundary. These are not classical white holes, but they're quantum cousins, hinting that the information escape route might exist in a blurred, probabilistic form. Then there is the grand cosmological vision of physicist Lee Smolin. He proposed a theory of cosmological natural selection, where new universes are born inside black holes. In this stunning cycle, when a black hole forms in a parent universe, the extreme conditions at its singularity spark a new Big Bang, creating a child universe with slightly different physical constants. This child universe expands within its own spacetime, disconnected from the parent. Here, the birth of the new universe is by definition a white hole event. All the information that fell into the parent black hole, scrambled and transformed, becomes the seed for the new cosmos. The white hole is not an object in space, but the beginning of space itself, carrying forward the genetic information of its parent. In all these speculative frameworks, the white hole concept transitions from a mathematical curiosity to a potential necessity. It becomes the universe's emergency exit for information, the cosmic recycling plant, or the birth canal for new realities. It is the mechanism that allows the story to continue, ensuring that no chapter, no matter how chaotic, is ever truly lost. The information paradox forces us to confront the possibility that space-time, at its most extreme, is not a static stage but a dynamic, living process. And in that process, the line between a black hole's end and a white hole's beginning may be the most important line of all. This cosmic recycling idea finds its most rigorous form in the cutting-edge quest to unify physics. White holes are not just a fun speculation, they have become a critical testing ground for the most ambitious theories of all, those attempting to craft a theory of quantum gravity. For decades, physicists have sought to marry the vast, smooth spacetime of Einstein's general relativity with the frantic, granular quantum world. Where these two theories meet at the heart of a black hole or the moment of the Big Bang, our current math breaks down into infinities. Something new must take over, and in several leading candidates for this new theory, white holes emerge not as optional ideas but as necessary consequences. Take loop quantum gravity, often called LQG. This framework proposes that spacetime itself is not a continuous fabric, but woven from tiny, finite loops, a kind of quantum tapestry. One of its most stunning predictions is that the terrifying singularity, the point of infinite density predicted by Einstein's equations, does not actually exist. Instead, quantum gravity acts like a cosmic repulsive force. Imagine a collapsing star reaching the final moment of crunch. In classical physics, it vanishes into an infinitely small point. But in loop quantum gravity, as the density approaches the unimaginable Planck scale, those quantum loops of spacetime push back. The collapse doesn't end in a dead-end singularity. It rebounds. This is the black hole to white hole transition. The matter that fell in reaches a point of maximum compression and then, governed by quantum geometry, begins to re-expand. The one-way trap of the black hole event horizon would, over an extremely long time, transform into the one-way eruption of a white hole horizon. The tunnel doesn't lead to another universe, it leads to the future of the same matter, spewing it back out after a quantum pause. In this view, a black hole is not an eternal grave, it is a temporary state of ultra-dense hibernation. What we call a singularity is actually a bridge, a quantum bridge, connecting the black hole phase to the white hole phase. The information that fell in isn't lost, it's just undergoing an incredibly slow processing before being returned to the cosmos. The lifetime of such an object would be staggering, far longer than the current age of the universe for a stellar mass black hole, placing the white hole eruption in the almost mythical distant future. String theory, another great contender for a unified theory, also finds roles for white holes in its complex landscape. In some string theory models, the specific arrangement of the extra dimensions and branes can create objects that look and behave like white holes or produce effects akin to a white hole's explosive output. They appear in the math as stable or metastable configurations, potential endpoints for cosmic evolution. While the details are profoundly technical, the consistent theme across these theories is remarkable. When you push our understanding of reality to its absolute limits, to the place where gravity becomes quantum, the rigid classical concepts of black holes and white holes begin to blur and merge. They become two phases of a single quantum object, two sides of a transformational coin. The white hole is no longer the impossible rebel against thermodynamics. In the quantum gravity picture, it is the universe's way of preserving its deepest rules, of ensuring that no story, not even the story of something falling into a black hole, ever truly has a final period. It is the ultimate plot twist written into the code of spacetime itself. The universe seems to have a clear recipe for creating a black hole. Take a massive star, let it burn through its fuel, and watch its core collapse under its own immense gravity. It is a violent, chaotic, but perfectly natural astrophysical process we have observed and understood. But for a white hole, the recipe book is completely blank. There is no known chain of events in our current universe that could naturally assemble a region of space-time where matter is forbidden from entering. If a white hole cannot form, then its existence as a physical object becomes an even deeper puzzle. So where could it possibly come from? The leading answer points us back to the very first moments of everything. White holes, if they are real, are almost certainly not born from dying stars. They would have to be primordial. This means they would not form within the universe as we know it, but would be artifacts woven into the fabric of space-time during its initial, ferocious expansion, perhaps within the first fraction of a second after the Big Bang. In that unimaginably dense and hot primordial soup, the very laws of physics were likely different, fluctuating wildly. Under those extreme conditions, tiny knots of space-time geometry might have pinched off, creating not just the hypothesized primordial black holes, but also their theoretical opposites. A white hole would not be something the universe makes, but something it was born with, a fossil from the moment of creation itself. But even if such a primordial white hole could pop into existence, it faces an immediate and potentially fatal problem, the instability problem. Think of a white hole's defining rule that nothing can ever cross its horizon from the outside. Now imagine a single speck of interstellar dust, a tiny hydrogen atom, drifting through the void and gently bumping into that horizon. According to the classical equations, that atom cannot enter, but it carries energy, and energy warps space-time. The moment that atom interacts with the white hole's gravitational field, it effectively adds a tiny bit of mass to the system. In the bizarre logic of general relativity, adding any external mass or energy to a white hole should, in theory, cause it to instantly collapse and transform into a black hole. Its perfect exit-only barrier would shatter, and it would become the very thing it was meant to oppose. This makes a classical white hole seem like a cosmic soap bubble, impossibly fragile, doomed to pop at the first contact with reality. Its existence would be fleeting, a momentary glitch that the universe immediately corrects. This instability is a major reason many physicists dismiss white holes as physically impossible objects. They appear mathematically but seem to require a perfectly sterile, empty universe to survive for even an instant. Our cosmos is not sterile, it is filled with dust, light, and the faint whisper of radiation from the Big Bang itself. A primordial white hole would have been bombarded from the moment it appeared. So how could it possibly last for billions of years? The answer might lie beyond Einstein's classical equations in the quantum realm. Perhaps the white hole's horizon is protected by quantum effects, a subtle barrier that repels incoming matter not with infinite force but with quantum probability. Or maybe, as some theories of quantum gravity suggest, a white hole is not a separate object at all, but merely a phase in the life cycle of a black hole, a rebound that happens after an almost eternal duration. In that view, the white hole isn't waiting to be born, it is what a black hole becomes when it finally dies. This shifts the question from how one forms to how long we must wait to see one transform. This quantum bridge from collapse to re-expansion finds a powerful champion in the work of physicist Carlo Rovelli. He and his colleagues have developed a specific, compelling model within loop quantum gravity that gives the white hole a concrete, if distant, place in our cosmic future. Their calculations suggest an astonishing fate for the black holes we see today. Given enough time, a time so vast it makes the current age of the universe seem like a single blink, an old black hole could undergo a profound metamorphosis. It would not simply evaporate away via Hawking radiation and vanish. Instead, through a process akin to quantum tunneling, the black hole could transform into a white hole. Think of it not as a classical object suddenly flipping a switch, but as a spontaneous quantum leap for the entire spacetime structure. The intense gravitational field at the black hole's core, governed by the granular quantum geometry of loop theory, would reach a point where a repulsive force takes over. The matter and energy that fell in eons ago would begin to re-expand. The event horizon, that perfect one-way membrane, would quantum tunnel into a new configuration, becoming an exit door. What was once the universe's ultimate trap becomes, over timescales we can scarcely comprehend, a source of new eruption. This white hole would not be a primordial fossil. It would be a reborn black hole, a second act written in the language of quantum probabilities. The implications of this are staggering. First, it means black holes are not eternal graves. They are temporary, albeit immensely long-lived, phases in the life cycle of matter. They are cosmic cocoons. Second, it paints a startling picture of the far, far future of the cosmos. Imagine a universe trillions upon trillions of years from now, cold and dark, its stars long dead. In this profound silence, the last remaining structures would be these ancient black holes slowly turning inside out. One by one, across the unimaginable gulf of deep time, they would light up with slow-motion white hole explosions, each a final burst of energy and information returning to the void. The universe would not end with a whimper, but with a series of delayed quantum fireworks, the last echoes of everything that ever fell in. Ravelli's work moves the white hole from a mathematical ghost to a potential endpoint predicted by a serious theory of quantum gravity. It offers an elegant solution to the information paradox, as the data swallowed by the black hole is preserved through its transformation and eventually released. In this vision, the cosmos itself possesses a built-in recycling mechanism, operating on a timescale so grand it redefines our understanding of forever. That quantum rebirth in the far future is a breathtaking vision, but there is another, more immediate puzzle where white holes might play a hidden role. We have been searching the cosmos for the source of dark matter for decades. This invisible substance makes up over 80% of the matter in the universe, binding galaxies together with its gravity, yet it refuses to emit or absorb light. We know it is there by its effects, but we have no idea what it is made of. All our searches for exotic particles have come up empty. Could the answer be not a particle at all, but a relic from the dawn of time? This is the speculative leap that primordial white holes might be a constituent of dark matter. Think about the properties dark matter must have. It has to be massive to exert gravitational pull. It must not shine, or we would see it, and it must interact with ordinary matter and light only through gravity, otherwise it would have revealed itself by now. Now consider a microscopic white hole born in the first instance of the universe. It is not made of atoms or any known particles. It is a knot of pure spacetime geometry. It would have mass bending the space around it. It would be completely dark, emitting no light of its own unless it was in its death throes. And because its defining feature is a horizon that repels entry, it would barely interact with anything. A stray proton or photon would simply bounce off its gravitational influence, never merging with it. A cloud of such objects scattered throughout a galaxy would provide the perfect gravitational scaffolding, invisible and untouchable. They would be the universe's ultimate ghosts, not made of matter, but of the very fabric of reality, acting as anchors for the stars we see. This idea elegantly solves one problem with another. The mystery of dark matter meets the mystery of the white hole. But of course, the challenges are immense. The classical instability problem looms large. How could these white holes survive for billions of years without collapsing into black holes from random collisions with cosmic dust? proponents suggest quantum effects might stabilize them, placing them in a kind of suspended animation. More pressingly, if they are primordial and have been around since the beginning, why aren't they exploding? The gamma-ray burst signature we discussed earlier would be their final act. Their absence in our observations could mean they are perfectly stable, or that they evaporated via a process akin to Hawking radiation long ago, leaving nothing behind. This is why the idea remains on the fringe of cosmology. It is a beautiful hypothesis that fits some key criteria, but it introduces new questions just as difficult as the one it tries to answer. Yet, in a field filled with unknowns, it serves a vital purpose. It forces us to expand our imagination beyond particles and forces, to consider that the missing mass of the cosmos might not be a new form of stuff, but an ancient echo of spacetime itself, a fossilized remnant of creation's first strange breath. Such a cosmic recycling machine forces us to confront the very nature of time itself. Our daily experience tells us time has a clear, irreversible arrow. An egg can scramble, but it will never unscramble itself in the pan. This one-way flow from order to disorder is the bedrock of our reality. Yet the mathematics of white holes as perfect mirrors of black holes treats time with a stunning indifference. The equations of general relativity are time-symmetric, meaning they work just as well if you run the clock backwards. In that reversed view, a black hole swallowing a star becomes a white hole erupting one. This symmetry suggests that at the deepest, most fundamental level, the universe's laws do not care which direction time flows. The arrow we feel so strongly might not be written into the code of physics, but could emerge from something else, perhaps from the specific, low entropy conditions of the Big Bang itself. If white holes are real, they are a glaring reminder of this hidden symmetry, a crack in our perception where time's true neutrality might show through. This leads to a dizzying possibility known as retrocausality. Some speculative models involving white holes and quantum gravity allow for effects to precede their causes. Imagine a white hole eruption in the distant future somehow influencing the formation of a galaxy in the past. It sounds like pure fantasy, a violation of everything we know. But if time's arrow is not fundamental, then the rigid chain of cause and effect we rely on might be a local rule, not a cosmic law. Our present might be shaped not only by the past, but by whispers from the future, channeled through these bizarre space-time structures. While there is no evidence for this, the mere fact that such ideas emerge from serious theoretical work tells us that white holes are not just astronomical objects, they are philosophical provocations. They challenge our most basic assumptions about how reality is structured. They force us to ask if the universe is a single, linear story, or a more complex tapestry where beginnings and endings are woven together in a loop. This brings us to the grandest cycle of all, the fate of the cosmos. For decades, cosmologists have debated whether our universe will expand forever into a cold, dark emptiness, or eventually reverse course in a big crunch, collapsing back into a fiery singularity. White holes offer a startling bridge between these two endings. In a big crunch scenario, the entire universe collapses under its own gravity. What happens at that final, singular moment? If loop quantum gravity is correct, that ultimate singularity might also rebound. The big crunch would not be an end, but a transformation. The entire cosmos, having fallen into its own gravitational well, could experience a quantum bounce and erupt anew in a new Big Bang. In this breathtaking vision, our universe is just one phase in an endless cycle of expansion and contraction. And each new Big Bang is, by definition, a white hole event on a cosmic scale. The white hole is not an object within the universe, it is the universe being reborn from the ashes of its previous incarnation. This cyclical model provides a profound kind of cosmic immortality. No information is ever lost, it is simply recycled through these phases of collapse and eruption. every galaxy, every star, every life that ever existed in a past cycle leaves its imprint, scrambled into the fundamental quantum fields to potentially influence the next. We are not just stardust, we are the recycled material of countless previous universes. Pondering white holes ultimately pulls us far beyond astronomy. It asks us to consider whether the universe is a one-time experiment or an eternal breath. It questions if our experience of time is a universal truth or a beautiful local illusion. These are not questions with easy answers, but they are the kind of questions that remind us why we look up at the stars in the first place, not just to map the heavens, but to understand our place within a story whose scale and plot we are only beginning to glimpse. Visualizing these cosmic enigmas requires a leap into digital worlds. Since we cannot point a telescope at a white hole, scientists and artists turn to the power of simulation, using the equations of general relativity to paint a picture of how such an object would warp the very light around it. The key difference lies in the direction of the distortion. A black hole's immense gravity acts like a cosmic funnel, bending light rays inward and trapping them, creating its iconic dark shadow ringed by a twisted halo of light. A white hole, by its repulsive nature, would do the opposite. It would push spacetime outward, bending light rays away from its horizon. Instead of a dark shadow, we might see a brilliant, distorted region, a kind of blinding flash in space where light is scattered and magnified in chaotic patterns. Imagine two simulations side by side. On one side, a black hole with a neat, flat accretion disk of superheated gas spiraling inward in a smooth, fatal ballet. On the other, the white hole presents pure chaos. There is no orderly disk falling in. Instead, we might see a violent, turbulent outflow, like a geyser of radiant matter erupting in all directions, its light bent and smeared by the fierce, repulsive gravity into a shimmering, unpredictable aureole. These visualizations are more than just pretty pictures, they are rigorous thought experiments. They show us that if a white hole did exist, it wouldn't just be a black hole running in reverse. It would create an entirely new and spectacular kind of optical illusion in the cosmos, a beacon of distorted physics screaming its presence across the void. That shimmering digital beacon is a powerful image, but it has also given rise to persistent myths. One of the most common misunderstandings is the idea of anti-gravity. A white hole is not a region of repulsive gravity pushing everything away like some cosmic magnet. It possesses immense normal gravitational pull, just like any massive object. If you were in a spaceship near one, you would feel its powerful tug pulling you toward it. The magic and the paradox is not in the gravity itself, but in the nature of its event horizon. You could be pulled right up to that boundary, but you could never cross it. The laws of physics as we model them would make that horizon an impenetrable wall from the outside, a cosmic checkpoint where the direction of travel is permanently set to out. It's a one-way exit door set in a deep gravitational well, which is what makes the concept so counterintuitive and difficult to reconcile with our experience. Another crucial clarification is that white holes are not proven. They remain a spectacular theoretical possibility, a ghost in the machinery of Einstein's equations. No telescope has ever confirmed their existence. They are a what-if of the highest order, a tool for stretching our understanding to its breaking point to see what might lie beyond. This also means they are almost certainly not the other end of every black hole you see in the night sky. The elegant mathematical bridge connecting a black hole to a white hole in another universe is a pristine, ideal structure. The real, messy, astrophysical black holes formed from collapsing stars are surrounded by swirling matter and radiation, conditions that almost certainly destroy any such delicate wormhole connection. The black hole at the center of our galaxy is not a tunnel to somewhere else, it is almost definitely a final destination. Finally, there is a tempting but overly simplistic shorthand calling a white hole a time-reversed black hole. While the mathematics are symmetric, the physical reality is not so trivial. Running time backwards for a cup of coffee shattering on the floor shows you the pieces flying up to reassemble. That is mathematically possible, but thermodynamically absurd in our universe. The same profound issue exists here. A white hole isn't just a black hole video played in reverse, because that reversed video would show a universe violating the second law of thermodynamics, with order magically appearing. The distinction is causal and thermodynamic. A real white hole, if it could exist in our causal future, would have to find a way to be born, to erupt without having a past that violates those fundamental rules. It forces us to confront the difference between mathematical time symmetry and the irreversible arrow of time we actually live within. These misconceptions matter because clearing them away reveals the true, staggering strangeness of the idea, not as a simple cosmic opposite, but as a profound challenge to how we think about time, creation, and the very structure of reality. The elegant symmetry of Einstein's equations is undeniable, but for many physicists that is precisely where the problem lies. Mathematics can describe countless worlds that do not and cannot exist. A universe where time flows backwards is mathematically sound, but it is not our universe. For prominent skeptics, white holes fall squarely into this category, a beautiful mirage with no physical water. Their primary argument is brutally simple thermodynamics. Our cosmos obeys the second law, marching relentlessly from order to disorder. A white hole, as a spontaneous source of low entropy order, would be a glaring violation of this most fundamental rule. It would be like finding a waterfall that consistently flows uphill, defying gravity not with a pump but by its very nature. The universe, they argue, does not permit such rebellious objects, it immediately corrects them. Any interaction with external matter, even a single photon, should cause a white hole to collapse into a black hole, erasing its defining characteristic in an instant. From this perspective, white holes are not just unstable, they are impossible mathematical ghosts we should not expect to find in the real, messy cosmos. This skepticism is bolstered by powerful alternative frameworks that solve the same puzzles without invoking white holes at all. Take the famous no-hair theorem. It states that a black hole from the outside can be completely described by just three properties: its mass, its electric charge, and its spin. All other information about the material that formed it, the type of star, its composition, whether it swallowed planets or spaceships, is lost, shaved off as it settles into its final state. This theorem long supported the idea of true information loss, but modern physics has evolved. The leading alternative today is the holographic principle, a concept so radical it reimagines the nature of reality. It proposes that all the information contained within a three-dimensional volume of space, like the interior of a black hole, can be perfectly encoded on its two-dimensional boundary, the event horizon. Think of it like a cosmic DVD. The rich, three-dimensional movie of everything that fell in is not destroyed. It is compressed and stored on the surface of the black hole itself, like data etched onto a disk. When Hawking radiation slowly bleeds energy from the black hole, this information is subtly imprinted on that radiation, eventually released back into the universe as the black hole evaporates. In this view, there is no need for a white hole tunnel, a quantum bounce, or a bridge to another universe. The information never truly enters the black hole's interior in a way that requires escape. It is preserved on the horizon from the start and leaks out over eons. This framework has gained immense traction, offering a path to resolve the information paradox within the bounds of quantum mechanics and without the causal nightmares of white holes. The debate, therefore, is not a minor technical dispute. It is a fundamental fork in the road for theoretical physics. On one path, you have the time-symmetric elegance of general relativity extended to its logical, if bizarre, conclusion, giving us white holes, wormholes, and cosmic rebirth. On the other, you have the uncompromising arrow of thermodynamics and the holographic encoding of quantum information. painting a picture where black holes are their own self-contained information processors with no exit door required. Which path describes our reality? The truth is, the physics community does not have a consensus. It is a vibrant, ongoing argument fought with equations and thought experiments. The white hole remains a powerful conceptual tool, a stress test for our theories. Even if it never manifests as a real object in the sky, its value is immense. It forces us to ask the hardest questions about time, information, and the origin of everything. By wrestling with its impossibility, we might just stumble upon the next great leap in understanding the universe. This relentless debate between elegant symmetry and irreversible law brings us to the most profound speculation of all. Could the white hole be the universe's ultimate reset button, not for a star or a galaxy, but for everything that exists? Imagine our cosmos not as a one-time event, but as a single heartbeat in an eternal cosmic rhythm. This is the vision of cyclic universe models, and the white hole sits at their very core. The most dramatic version begins with a big crunch. After trillions of years of expansion, gravity finally wins. Every galaxy, every particle reverses course, rushing back toward a single, catastrophic point. According to classical physics, this ends in a final, all-consuming singularity, a full stop to reality. But if the principles of quantum gravity, like those in loop theory, are correct, that singularity is not an end. At the moment of maximum compression, quantum effects could trigger a rebound. The entire universe, having collapsed into what looks like a black hole of cosmic proportions, would then explode outward in a new Big Bang. That moment of explosive rebirth is, by its purest definition, a white hole event on the grandest possible scale. Our entire universe, in this breathtaking view, would be the output from a white hole that was once the black hole finale of a previous cosmos. We are not the first chapter, we are the next verse in an endless poem, with white holes as the punctuation between stanzas. A more subtle and mathematically sophisticated version of this cycle comes from the renowned physicist Roger Penrose. His conformal cyclic cosmology, or CCC, proposes a cycle not of collapse and explosion, but of infinite expansion and graceful transformation. In Penrose's model, our universe will expand forever, but over timescales so vast they defy comprehension. All matter will eventually decay, black holes will evaporate via Hawking radiation, and the cosmos will become a cold, empty sea of massless particles like photons and gravitons. In this state, something remarkable happens. The universe loses all sense of scale. An infinitely large, empty, cold space becomes geometrically identical to an infinitely small, hot, dense point. The far future of one cycle smoothly connects to the ultra-hot beginning of the next. There is no violent crunch, just a conformal rescaling, a cosmic reset where the end seamlessly becomes a new beginning. And what sparks that new beginning? It is an eruption from the past. In Penrose's vision, the total evaporation of all black holes in the previous eon does not just release energy, it releases information in the form of low-frequency gravitational waves. When the next cycle begins with its new Big Bang, these echoes from the previous universe manifest as imprints on the very first light, the cosmic microwave background. Penrose calls these imprints Hawking points, circular patches of slightly higher temperature. He proposes these are the final, faint signatures of supermassive black holes from the previous eon, their evaporated energy and information now etched onto the sky of the newborn universe. And what is the process that takes the evaporated remains of an ancient black hole and imprints it onto the birth of a new cosmos? It is, in essence, a white hole mechanism. The information is not destroyed, it is processed through the end of time and then injected back in at the beginning. The white hole becomes the cosmic transfer mechanism, the channel through which the story of one universe whispers into the fabric of the next. While most cosmologists remain skeptical of the specific evidence, the power of Penrose's idea is undeniable. It elegantly uses the white hole concept not as a literal object in space, but as a fundamental principle of cosmic rebirth. It suggests that creation and destruction are not opposites, but part of a single, eternal process, with the white hole as the transformative link in an infinite chain. To consider this is to look at the night sky and wonder if every galaxy we see is but a temporary pattern in an everlasting flame, a flame that is constantly being extinguished and rekindled by the most profound physics we can scarcely imagine. Harnessing a white hole would be the ultimate act of cosmic engineering. Think of the sheer power involved, a region of space-time violently expelling matter and energy from its very core. It presents itself as the universe's perfect battery, an infinite energy source, but this fantasy immediately slams into the law of energy conservation, one of the most fundamental rules in all of physics. Energy cannot be created from nothing, it can only change forms. A white hole wouldn't be creating energy, it would be a channel, a release valve for energy that was stored somewhere else, perhaps in a previous cosmic cycle or a connected black hole. Tapping it would be less like inventing a perpetual motion machine and more like plugging into the Big Bang itself, a prospect as terrifying as it is tantalizing. The energy output would be unimaginable, raw and chaotic, likely vaporizing any technology we could dream of building near its horizon. Then there's the dream of travel. If a white hole is the exit of a wormhole, could it be a gateway? The idea is irresistible, a one-way ticket to another star system or another universe entirely. We could fling a probe into a black hole here and have it emerge from a white hole light years away, seemingly breaking the universal speed limit. Yet this ignores the brutal reality of the journey. The wormhole bridge is almost certainly unstable, collapsing instantly. Even if it held, the tidal forces and radiation at the center would shred any known material into its fundamental particles. You wouldn't arrive anywhere, you'd be transformed into a burst of scrambled information. The white hole as a stargate is a beautiful story, but physics tells a far more destructive tale. Perhaps a more practical, if equally fantastical, use would be waste disposal. Imagine containing our most dangerous byproducts, our nuclear waste, and hurling it into a nearby black hole. The linked white hole, in theory, would then eject it into some other realm, permanently cleaning our cosmic house. It's the ultimate out-of-sight, out-of-mind solution. But this, too, is fraught with peril. We have no control over where or when that material would reappear. Our toxic garbage could erupt into a pristine alien ecosystem billions of years in the future, or worse, it could violate causality, its exit preceding its entry in a dizzying temporal loop. We would be solving one problem by creating an unpredictable, potentially universe-breaking paradox. These technological daydreams, while impossible with our current understanding, serve a vital purpose. They are not blueprints but stress tests. By playing with the idea of harnessing a white hole, we vividly illustrate the extreme properties it must possess, and in doing so, we better understand the laws it would shatter. It forces us to confront why energy conservation is sacred, why faster-than-light travel is forbidden, and why causality cannot be toyed with. The white hole in these fantasies becomes a mirror. We gaze into it, dreaming of infinite power and endless frontiers, and what stares back is the immutable framework of reality itself, reminding us that some doors are not meant to be opened. That vision of an eternal cosmic cycle forces us to look at our own universe's accelerating expansion in a startling new light. We call the mysterious force behind this acceleration dark energy, and it makes up the vast majority of the cosmos. But what if dark energy is not a new, exotic field, but a ghostly echo of a white hole process happening everywhere at once? This is not a mainstream theory, but a few speculative papers have dared to connect these two profound mysteries. They propose that the repulsive, expansion-driving nature of dark energy might be a diffuse, universal manifestation of the same principle that defines a white hole, a gentle but relentless push from the fabric of spacetime itself. Imagine the white hole's defining trait, that fierce repulsion at its horizon, not concentrated at a single point, but smeared across the entire universe. Instead of a violent eruption from one location, it would be a smooth, all-pervasive pressure gently stretching the cosmos apart from within. In this highly speculative view, the Big Bang wasn't just a one-time white hole event, it was the beginning of an ongoing white hole phase. We are not living in the aftermath of an explosion, we are still inside the explosion, and dark energy is the continuing outward pressure of that initial creative act. This idea attempts to link the largest-scale behavior of the cosmos, its accelerating expansion, with the most extreme small-scale physics of quantum gravity that might govern white holes. It suggests that the universe's fate is written not by a mysterious dark energy particle, but by the intrinsic, repulsive geometry of space-time as it continues to unfold from its primordial state. While this connection remains on the farthest fringe of cosmology, its value is in its sheer boldness. It demonstrates how the white hole concept refuses to be confined to a single astronomical puzzle. Instead, it sits at a thrilling intersection, forcing bridges between our deepest questions. It connects the nature of singularities, those points of infinite density, with the quest for quantum gravity, a theory to describe those singularities. And it directly influences our models for the ultimate fate of the cosmos, whether that fate is a cold, dark drift or a transformative rebirth. The white hole is more than a hypothetical object. It is a conceptual key, one that might unlock how the universe begins, how it evolves, and how it might one day begin again. This speculative bridge between dark energy and cosmic birth reminds us that some of our boldest ideas begin not in equations but in stories. The relationship between science fiction and theoretical physics is a two-way street where imagination fuels investigation. For decades, the vivid portrayals of wormholes and white holes in books and films have done more than entertain. They have educated and inspired. They have taken the dry, intimidating mathematics of general relativity and given it a face, a sense of wonder, and a narrative stakes that pure theory often lacks. When a viewer watches a spaceship vanish into a swirling vortex or emerge from a radiant gateway, they are not just seeing special effects, they are being introduced to a genuine concept from the edge of human knowledge. This public fascination creates a cultural appetite for discovery, pushing these ideas from the fringe of physics into mainstream conversation, and sometimes into the minds of the next generation of scientists. Consider the very term exotic matter. To a physicist, it describes a hypothetical substance with negative energy density, something that could, in theory, generate a repulsive gravitational effect. This isn't fantasy, it emerges from certain solutions in quantum field theory. But its most famous proposed application, stabilizing a traversable wormhole to prevent its instant collapse, was popularized and explored in depth through science fiction long before it became a standard part of theoretical discourse. The idea migrated from the pages of novels and the scripts of screenplays into serious scientific papers, bringing with it a shared language and a set of visual metaphors that researchers could use to communicate complex ideas. Science fiction provided the thought experiment, a narrative framework asking, what would we need to make this work? Physics then attempts to answer, often finding that the requirements, like exotic matter, are even stranger than the original fiction imagined. This creative symbiosis is why white holes, even as unproven speculation, are vital to cosmology. They are a catalyst for creative thought. By insisting we take the mathematics of Einstein to its most extreme logical conclusion, even when that conclusion seems to defy common sense, we are forced to confront the weaknesses in our understanding. A physicist imagining a universe where white holes are real must immediately grapple with thermodynamics, with causality, with the nature of time itself. The white hole becomes a philosophical sandbox, a tool for stress testing the foundations of reality. It asks the big, messy questions that strictly incremental science sometimes avoids. What is time? Where did everything come from? Could the laws of physics be different? Science fiction, by dramatizing these questions, keeps them alive in our collective consciousness, ensuring they remain targets for rigorous investigation. So the next time you see a glowing portal in a starfield, remember, you are not just watching a story, you are witnessing a dialogue, one where the wildest dreams of storytellers and the most precise calculations of scientists meet to redraw the map of the possible. The universe's grandest mysteries often feel distant, but sometimes the best way to grasp them is through a direct conversation. So let's sit down with a physicist, a composite of many brilliant minds working on the edge of known physics, and ask the questions you might be thinking right now. First, the big one: will we ever actually see a white hole? It is the most unlikely detection in all of astronomy, but we cannot rule it out completely. The signature would be unmistakable, a cataclysmic flash of high-energy radiation appearing from a seemingly empty patch of sky, with no collapsing star or colliding neutron stars to explain it. We have telescopes constantly scanning for such events. If we ever saw one that defied every conventional model, that had no remnant, and that came from the void, well, that would force us to take the white hole hypothesis from the fringe to the forefront overnight. But we must be honest, the odds are vanishingly small. The universe seems to have a strong preference for black holes. What would happen if I tried to fly a spaceship into one? You would fail spectacularly. Think of it not as a hole you can enter, but as a wall of pure force. As you approach, the gravitational pull would be immense, just like near a black hole of similar mass. But as you got closer to the event horizon, the physics becomes bizarre. The space-time curvature itself would act as an impenetrable barrier, repelling you. Your ship would be violently buffeted by the torrent of radiation and matter erupting from within. Long before you could even contemplate crossing the boundary, you would be torn apart by the extreme forces or vaporized by the energy. It is not a doorway, it is a cosmic fortress wall with its cannons perpetually firing outward. The formation problem seems insurmountable. How could one even come to be? This is the core of the skepticism. In our current, mature universe, there is no known natural process that creates an exit-only region of spacetime. My best guess, if they are real, is that they are not made but inherited. They would be relics, fossils from the first instance of the Big Bang, when the laws of physics were being written. A tiny quantum fluctuation in the primordial foam could have pinned a region of spacetime into this white hole configuration, a cosmic typo that somehow survived. Or, as some of my colleagues working on loop quantum gravity suggest, they are not born but reborn. An ancient black hole, after a time so long it numbs the mind, could undergo a quantum transition and become a white hole. So we are not looking for something that forms, but for something that either always was or something that has finally become. Do you personally believe they exist? I believe in the mathematics that predicts them. Einstein's equations are too beautiful and too consistent to ignore this symmetric possibility. But belief in the math is different from belief in a physical object in our sky. My heart wants them to be real because they tell a more interesting, more cyclical story about the cosmos. They suggest rebirth over oblivion. My head, however, is held in check by thermodynamics and the stark lack of evidence. So I occupy a middle ground. I work with the concept not as a fact but as the most powerful probe we have. By asking what a white hole requires, we are really asking about the nature of time, the fate of information, and the validity of quantum gravity. Even if we never find one, the search forces us to build better theories of everything. In that sense, the white hole already exists, not out there in the stars, but here as an indispensable tool for thought. It is the question that keeps us humble and hungry. The physicist's words hang in the air, a testament to the power of a question still searching for its answer. This is where the story accelerates, moving from pure theory into the realm of tangible upcoming tests. The future of white hole research is not a passive wait for a lucky sighting. It is an active hunt, and the tools for this hunt are being built right now. On the cosmological scale, our ears to the universe are about to become vastly more sensitive. The Laser Interferometer Space Antenna, or LISA, is a revolutionary mission slated for the 2030s. Instead of detectors on Earth, it will consist of 3 spacecraft flying in a giant triangle, millions of kilometers apart, using lasers to measure the fabric of spacetime itself. LISA is designed to listen for low-frequency gravitational waves, the ripples from events too massive and slow for our current observatories to catch. This is where the exotic signature might appear. When 2 black holes merge, they create a specific gravitational wave chirp, a ring-down that fades in a predictable way. But some quantum gravity models, including those predicting black hole to white hole transitions, suggest a subtle difference. The event horizon might not be the perfect final membrane we think it is. Instead, it could have a quantum structure, a fuzziness, or a potential barrier. This could cause the gravitational wave signal to echo, with tiny, repeating whispers following the main crash. LISA, with its exquisite sensitivity, could detect these faint echoes. If it hears them, it wouldn't just confirm a white hole transition. It would be the first direct evidence that black holes are not classical objects but quantum entities. Each echo would be a fingerprint of quantum gravity at work, a clue that the old picture of a simple, empty horizon is wrong, and that something far stranger, perhaps a bridge to a white hole phase, is waiting in the mathematics. Parallel to this astronomical listening, another frontier is exploding in virtual space, the power of quantum gravity simulations. Researchers are not waiting for the universe to provide answers, they are building digital universes to test them. Using supercomputers, teams are running complex simulations based on the equations of loop quantum gravity and other candidate theories. They start with a simulated collapsing star, watch it form a black hole, and then let the quantum geometric effects play out over incredible simulated timescales. The goal is to see if and how the rebound happens. Does the singularity resolve? Does the event horizon quantum tunnel into a new state? These simulations are like digital time lapses of a cosmos, compressing billions of years into hours of processing. They are searching for the precise conditions under which a black hole might cease to be a black hole and begin its transformation. The data from these simulations can then be translated into specific, observable predictions. What would the gamma-ray flash of a microscopic white hole death look like? Exactly what frequency should LISA listen for in those echoes? By simulating the birth cries and death rattles of these theoretical objects, scientists are creating a wanted poster for the cosmos, detailing exactly what we need to find. Ultimately, cracking this mystery will demand a unification of perspectives that have long been separate. The answer will not come from astrophysics alone or from quantum theory working in isolation. It demands a conversation between the very large and the very small. Cosmology, the study of the entire universe's evolution, provides the stage, the dark energy, the black holes, and the cosmic microwave background where primordial whispers might be imprinted. Quantum physics provides the script, the rules that might govern the transformation of spacetime itself at the tiniest scales. A potential white hole signature in a gravitational wave is a quantum event writ large across the cosmos. A pattern in the ancient light of the Big Bang might be the holographic imprint of a previous universe's quantum evaporation. The next decade of discovery will be about building translators between these two languages. When LISA hears a ripple, quantum gravity simulations must explain its origin. When a telescope sees an inexplicable flash, cosmologists must determine if it fits into the life cycle of a reborn black hole. We are approaching the day when an observation from the largest scales will directly constrain a theory of the smallest scales, and vice versa. The white hole, this spectacularly improbable idea, sits at the crossroads of that conversation. It is the hypothetical bridge that connects the fate of a single, collapsing star to the ultimate fate of everything, urging us to look deeper, listen more carefully, and dare to simulate the impossible. Our journey has taken us to the very edge of what physics can describe. We have followed a symmetrical idea from the quiet pages of mathematics out into the roaring chaos of the cosmos. White holes emerge as a perfect mirror, a beautiful answer to a question the universe may not actually be asking. They are a testament to the power of human thought, to our refusal to accept that the story must end with a dark, silent period. We have seen how they transform the Big Bang from a singular event into a possible white hole eruption, the original creative act. We have watched them become potential saviors in the information paradox, offering a cosmic escape route for data seemingly doomed to oblivion. And we have witnessed them become essential playgrounds for the boldest theories of quantum gravity, the testing grounds where spacetime itself might be seen to breathe in and out. Yet for all their elegance, they remain shrouded in profound doubt, challenged by the unyielding arrow of time and the deafening silence of our telescopes. They are the most beautiful impossible thing, a concept that may never be real, yet one we cannot afford to stop imagining. For in chasing these ghosts in the equations, we are not just searching for objects in the sky. We are probing the deepest rules of existence, asking if the universe is a one-way street or an endless loop. And in that relentless questioning, we come closer to understanding our own place within the mystery. That final, distant flash of quantum rebirth is where our story must rest. Picture a cosmos so old it has forgotten the concept of a star. The universe is a silent, frozen expanse, a sea of darkness stretching toward infinity. In this profound and endless night, the only structures left are the ancient black holes, themselves relics of forgotten galaxies. They have been evaporating for eons through Hawking radiation, growing smaller and fainter. And then, for one of them, a moment arrives that defies our classical understanding of time. After quadrillions upon quadrillions of years, the quantum geometry at its core triggers the transition. The black hole, the universe's ultimate endpoint, undergoes its final metamorphosis. In a flash of energy that briefly pierces the eternal dark, it turns inside out. What was a perfect trap becomes a sudden, brilliant source. It is a white hole erupting for the first and last time, its energy and information spraying back into the void. This isn't an end, but a seed. That single eruption could be the first note in a new symphony of physics, the initial fluctuation in a fresh cosmic cycle, the spark for a new Big Bang in a disconnected reality. Our universe may fade to black, but the story does not end. It reboots. This is the ultimate promise and the profound mystery of the white hole. It teaches us to embrace the not knowing. Some of science's most vital work is done not in proving what is, but in rigorously imagining what could be. These thought experiments, these beautiful impossibilities, stretch the fabric of our understanding until it reveals its true shape. They remind us that curiosity is not just about finding answers, it is about learning to ask better questions. So look up at the night sky with that spirit. Wonder about what might lie beyond the edge of our equations, in the white spaces of our maps. What do you think the universe's greatest secret might be? Share your own theories in the comments below, and if you want to join more journeys to the very edge of understanding, be sure to subscribe. The next mystery is always